Hello, everyone, and welcome back to the Engineering for the New Reality podcast series. There's been so much talk on 5G, electrical mobility, energy storage, and DC power, but the fundamental building blocks to making all of these things happen is power electronics. There are major shifts in the power needs across the world, which translates to a major shift in the way electronics are being engineered. To discuss a little bit more about the innovations that are happening in this industry and how LTTS can help, we have with us Atul Abhyankar, who heads our Power Electronics Engineering Division. Hi Atul, welcome to the podcast. How's it going?
Not too bad, Akshay. Good morning to you. How are you doing?
Very well, thank you. So Atul, in the power electronics industry, there's always been a fight for packing in more energy density, doing more with less. So, what are some of the new ways in which we can make our power electronics even more energy efficient? And how can LTTS help here?
Yeah, as you know, there is a saying that most of the things in the world of electronics, the viability of application is the power supply because it eventually leads to power requirements and energy utilization and powering of the equipments. So power supply is one of the heart, or I would say the main component of any electronics equipment which is being used. Traditionally, electronics equipment and electronics industry for ages has been trying to reduce the size, what we call as the form factor of the equipments. The glaring examples of these are the laptops, mobile phones, industrial equipments, which we see day in and day out. And if you compare the size of these equipments, it has gone southwards for last decades. And how does it impact power electronics? Because with this size, the size of the power supply that is powering these devices or equipments also has to be optimized to be in sync with the size of the equipment. And hence the form factor of the power supply has to go down. And as you go lower in size, you face the main issues that are like taking the heat away from the power supply, because that is one of the components of the equipment which generates a lot of heat. Hence, the focus on the development in power electronics is increasing the efficiency. The moment you increase the efficiency, less heat is generated and it's easier for the heat to be taken off. Hence, electromechanical packaging along with the new developments in power electronics is of utmost importance. So one of the ways to reduce the size is to increase the switching frequencies. Okay, but it comes at a cost. There is no free lunch. As you increase the switching frequencies, the switching losses go high, and also the magnetic losses go high. Of course, the size of the magnetics comes low because of a higher switching frequency, and thereby you can reduce the form factor. But if you reduce the form factor, you still have to take the heat away because the efficiencies may not go low. Okay, so one of the ways to do it classically was to use resonant conversion techniques of zero voltage switching and zero current switching. By doing this, what we do is we remove the losses associated in the switching phenomena of the power electronic devices. So yes, it did reduce the switching losses in the circuits, and we could push up the switching frequencies higher. We could also reduce the size of the magnetics, though magnetics losses did not go low, but new magnetic materials are evolving, which I'll touch on later. But to do that in a resonant circuits, you might have to put an extra tank circuits. So that was the only flip side. But yes, the designers were able to push up the frequencies higher, switching frequencies higher, and reduce the losses. New electromechanical packaging techniques, cooling techniques also have emerged over past couple of years, like liquid cooled converters is being a norm in electric vehicles. New fans with better speeds and higher air delivery have come, and new materials which bond the semiconductors to the heat sink using ceramics or aluminum oxide have actually helped in taking the heat away from the device. But the real future for increasing the frequencies is going to be tied up with the advancements in semiconductors. And for a long time, semiconductor industry has always fueled the advancements of power electronics. It started from thyristors, which needed a commutation circuit to turn it off, to GTOs, which could turn off without a commutation circuit, but needed a large amount of current to turn it off. Then came the BJTs or bipolar junction transistors, then MOSFETs, IGBTs, And in the recent past 5 years, wide bandgap devices have started entering the power electronics domain. The silicon carbide or SiC devices and gallium nitride or GaN devices are the ones which are catching up. Now, if you cue back to what I said about high switching frequencies and high losses, these devices are ideal to be operated at high frequencies because they have very low switching losses. They turn on and turn off very fast, and they can operate at a super high frequencies, which can actually reduce the switching losses when you jack up the frequencies. In addition, new magnetic materials, advancements in ferrites, materials like cool mu, MPP cores have come into picture which can withstand these high frequencies, because it's not in silo that conductors can go and have an advanced features, but the magnetics also should balance it so that the whole package of power electronics can be fit in a small package with a higher energy density and low losses, leading to higher efficiencies. If you ask me how LTTS can help, yes, we can help in a lot of ways. LTTS always believes in keeping up with the pace of the technology. And to do this, we have built our own internal accelerators using wide band gap FETs, like DC to DC converter, which is bidirectional, 10 kilowatt in power rating. We have designed using silicon carbide FETs, and we have achieved efficiencies greater than 96%. We have also designed a GaN FET based AC to AC converter, which takes the AC input and chops it down to a lower value without a transformer. Here we are operating at a frequency of around 300 kilohertz, and the whole unit is very compact. We also have an accelerator in terms of active front end rectifier unit, which is again built using silicon carbide devices running at 50 kilohertz. And the passives and the magnetics which are used here are very small compared to the classical AFEs for the same power rating, which operate at 10 kilohertz. In addition, LTTS also has a strong practice in computational fluid dynamics and electromagnetic simulations, so that we understand the best way of taking the heat out, the best way of cooling the critical components in the circuit. And the electromagnetic analysis helps us design the optimum magnetics. So all put together, we can give a solution to reduce the size and increase the power density.
And so, Atul, while there has been a slight delay in 5G rollouts, one can safely say that the rollouts are coming up soon and they're going to dramatically shift the way we function. So, how will this impact the power electronics industry and the way we engineer drives and converters?
Yeah, to answer this question, I will have to point to two aspects of how 5G will affect power electronics. One is what will happen to power electronics when 5G comes in terms of scaling up of the equipment which powers the power electronics. And number two is how power electronics equipments will change in terms of being more smart or being smarter after the arrival of power electronics. So as you know, the mobile industry has evolved from 2G to edge to 3G, 4G, and now 5G is coming. It's putative that 5G will be a part of the landscape in very near future. Now, what it does is when 5G comes in, all the receiving station, the transmitters and the base stations will need more power. They will need stronger power supplies. They will need to give more power to the 5G networks in the same size, in the same form factor. And this will fuel growth for new age power supplies to power up these equipments for 5G, for base station, for mobile towers if needed, and also for data centers where 5G will be of utmost use. And this will go hand in hand with the new age semiconductors, which will help drive the power densities up and give more efficient power electronic circuits to roll out the 5G equipment. So to answer the second aspect of what we spoke on how 5G will affect power electronics, currently power supply units, chargers, inverters and drives which are powering different loads like maybe enterprise communication load, the industrial loads, so on and so forth, are not fully digitalized. The reason is the northbound connectivity using 4G. Once 5G is in place, we can sensorize this the power supply units, the drives and inverters, which will be the main things in an automation industry, the motors, and take feedback from all these sensors and take the data and load it up to a cloud or a enterprise server using a 5G, because it will be available everywhere. Once this data is available, we can use analytics to find out the state of health of power supply, maybe which is charging the mobile towers itself, or which is or the power supplies that are charging, that are powering up the enterprise servers, or the inverters and drives, and try to find out if anything is going wrong in this equipment. For example, in power supply, the weak link is a capacitor, and if we can have proper sensor data to analyze the capacitor temperature, the ripple current through it, we can always predict when the capacitor, hence the power supply, will fail. Similarly, in the inverters, drives, or any power electronic equipment, if we see that suddenly the temperature rise is higher for a similar load, then we understand that something is going wrong somewhere, and then we can schedule a maintenance of this. And this will be possible by using the condition-based monitoring, and also some of the solutions what we have, which can be merged with the sensors and the 5G to load the data up. And last, up to now, the supervisory control of power supplies, it has been existing, but is at a very limited level. With 5G coming in and the network availability being anytime, everywhere, or ubiquitous, as we say, we can also get into supervisory control of power supply, either through UIs or mobile applications, so on and so forth.
So let's switch gears a little bit and talk about electrical vehicles. So, from deploying ceramics and lithium-ion batteries to fuel cells, there are all kinds of innovations happening for EVs, right? The major considerations still revolve around pricing, power density, weight, safety. So what do you see as the future roadmap of power electronics for EVs, and what is LTTS doing in this space?
Yeah, EV is a subject that has caught an imagination of a lot of people. And yes, EV is going to be the future. And if you ask me, the heart of EV is going to be power electronics. May it be hybrid, may it be full EV, power electronics is there to stay. Because if you see the EV vehicle, if you see the plain architecture of EV vehicle, you have batteries which are driving an inverter which run the motor, which make the car go ahead. Now, the architecture may sound simple, but the components to it, which actually fuel this or which drive this, are chargers. Chargers can be onboard chargers as well as offboard chargers. They need to be efficient. Especially the onboard chargers, they need to be efficient. They need to be light in weight, and they need to be ultra safe. Offboard chargers also, they need to be designed in such a way that the harmonics they generate, because believe me, the offboard chargers are going to have a high wattage, and I'll come to the wattage in 5 minutes at a later part of this question. And the harmonics which they might cause if not designed properly on the grid can be very high. In addition, there are going to be inverters which are going to drive the motors, and there are going to be auxiliary DC-DC converters. Now, if you go to each and every aspect of this, an interesting study evolves. If you look at if you start from the inverter side, okay, EVs are going to be of various types. You're going to have two-wheelers, you're going to have three-wheelers, you are going to have four-wheelers, which are, kind of Uber or Ola taxis. You are going to have high performance four-wheelers, SUVs, so on and so forth, and also e-buses and trucks. Now, if you see the two-wheeler and three-wheeler market, it's going to be totally different. The whole focus on two-wheelers and three-wheelers is going to be size, because the available space for mounting the chargers and the inverter is going to be very small. The power rating is not very high. The motors are not going to be, high-tech motors. So the challenge over there is in terms of power electronics is design something very cheap, which is efficient, and more so from the batteries point of view. The batteries which are going to be powering these have to be super reliable, and because two-wheelers and three-wheelers are predominant in Asian and tropical countries, temperature considerations are going to be an issue. Now, if you go to four-wheelers and Ola or Uber or a taxi kind of an application, what happens is the people who drive these cars are not so much interested in the performance of the car. They are not interested in going from 0 to 100 miles in 6 seconds. Rather, they want to have an inverter which is very, very efficient, and hence efficiency and how many miles you can go on a charge is going to be very important. So this market is totally different. If you go to a super high performance cars, then yes, you need inverters with very high digital controls, with very sophisticated digital controls, which can give a high starting torque, and then which can go into a high speed, low torque mode in a very smooth and an efficient way. And the performance of the inverters is going to be prime. And for buses, uh, the power of the inverters is going to be very high. So to fuel all this, you are going to need chargers. So if you look at two or three wheelers, the onboard chargers may not come on two or three wheelers. Rather, people would just carry a charger with them, and whenever they find a space, they will hook it up to a AC supply and charge their batteries. But for four wheelers, the typical power ratings what you're going to have for an onboard charger is going to be around 22 kilowatts or so. And of course, it's going to be higher up to 50 kilowatts for buses and trucks. And again, these onboard chargers will have to be liquid cool, because you have to pull the heat away from the car. Now coming to offboard charger, now this is a very interesting market, because most of the buses will be based on offboard charging. So you will need around greater than 300 kilowatt of pantograph charging for the buses or trucks, and greater than 600 kilowatts for fast charging. And believe me, it's going to put a lot of load on the current power system infrastructure which is existing. And to address all this, power electronics has to scale up, has to make things better, cheaper, and more efficient, and also cleaner from the point of view of transmission lines. Now, there are two other aspects to EV which are going to be addressing or going to be driving the power electronics. One is the battery. Currently, there are two lithium technology batteries. One is the LTO battery, good for quick charging, and lithium ion NMC, which is nickel magnesium batteries, which provides a high power output. And the energy density goal we would need to reach is 250 kilowatt at cell level and 200 kilowatt at module level, with 2000 cycles for charging. Further improvements in the battery technology are likely to come from solid state batteries by 2025 and metal air batteries. To achieve all this, the chargers, it's not going to be an easy job to replace the chargers. So the drive will be on making the chargers digitally controlled, where the charging algorithms for various different kind of batteries can be flashed on to the controller, and we need to make provision for this when we design the power electronic circuits with its controls, so that any new technology in battery which comes in, the power electronics should be able to cater to it. And last but not the least is the motors. So currently, if you see permanent magnet synchronous motors, induction motors, BLDC motors are being used in electric vehicles. Also switch reluctance motors, which are very good because they have got good speed torque characteristics and are basically easy to manufacture, and synchronous reluctance motors. So all these motors are being driven by the inverter. So the drive algorithm for the inverter to give the best possible torque, to give the best efficiency, has also got to be factored in. The new varieties of motors that are being investigated on is axial flux motors, and also the distributed motors, which will be in each of or call it distributed wheel drive, where you will have one motor per wheel. That is also being explored. It is also called as in-wheel motors. Another new motor technologies are going to be memory motors or flux switching permanent magnet motors. Now, all these will have to have a different types of algorithms for controlling. Yes, FOC or field oriented control is there to stay, but how you control is going to be different for various type of motors, and those things also have to be factored in when you are designing the inverters for the EV.
So, Atul, with so much talk about clean energy and meeting various sustainability targets, one of the biggest challenges for us still remains in building scalable and efficient energy storage systems, right? Because the thing is that installing storage, whether as a standalone asset or by adding to an existing utility power source, is still very individualized, and it doesn't interconnect with other sources of power. So, how can power electronics shape the future of energy storage and help us meet our clean energy goals?
Yeah, I think that's a very valid question because we discussed about 5G, which is going to need more power. We discussed about EV, which is going to change the landscape of the power requirements. So what is going to happen in near future? Suppose you have a bus station where you are charging 10 buses, and each bus needs say 600 kilowatts for quick charging. You're going to have a 6 megawatts of additional power requirement at that particular point. And what we need to ponder on is whether the power system which is installed in terms of the cables, the transmission lines, the circuit breakers, the transformers is equipped to handle this new energy load, which is going to be true for 5G, which is going to be true for EV, because you're suddenly going to see a large increase in the requirement for power coming up. So if you see the current CAGR for the home electric supply from 2018 to 2024, it is going to be 6.2%. And if you add EV and 5G to it, it's going to be much higher. And here is where power electronics will come into play. So what utility companies and the microgrid or the community, electrical community people do is, instead of beefing up the transmission distribution lines and these circuit breakers, which will cost for a lot of investment, what will be done is we'll have microgrids, and you'll have points where you will have renewable energies being connected to the grid. And to do that, what do you need? For renewable energy or the hybrid energy, where you take the energy from the renewables, store in the batteries, and then give it to the grid. For this kind of a energy storage system, the heart of it is again power electronics. You need voltage balancing converters to take the energy from the renewables, dump into the battery. The battery has to be tied to the grid, so you need an inverter. Also, if the power is available in the grid and excess power is available in the grid, there is no renewable, the inverter should be bidirectional. By saying that, what I mean is it should be able to take power from the grid and charge the batteries also. So for doing all this, we are the focus is going to be on highly efficient bidirectional inverters for tying to the grid, and inverters which will power up the batteries or charge the batteries from the renewables. So this is one of the areas where power electronics can help a lot. In addition, lot of loads are going to give bad current harmonics onto the transmission lines with bad power factor. It can be power factor hit because of harmonics or because of lagging or leading power factors. And another equipment in power electronics which can mitigate this is shunt active filters, which take the harmonics and negate them by introducing negative harmonics on the system, so that the power which is drawn is clean. And while doing so, the currents in the line go down because now the power factors improve, and whatever energy you are drawing is more of an active power than the reactive power. You need new generation power electronics converters and controllers to address this requirement. Okay, in addition, in the US, as you know, the distribution system has a pole mounted transformer which takes single phase and distributes it to the house. So there are multiple pole mounted transformers. So there is also a research going on having a distributed power inverter with battery pack near a pole mounted distribution transformer, or akin to a pole mounted distribution transformer, which can act as a means of reducing the peak load. So when you have this microgrid ready with different DERs, which is a distributed energy resource, plugged into different points of a power system, may it be for clean shaving, may it be for peak shaving, may it be for returning power to the grid or storing power to the batteries, this is going to change the landscape of the power system, and hence the requirements of the power electronics, which is going to fuel this clean grid and cater to a higher load demand.
So, Atul, to summarize, could you describe some of the differentiators of LTTS that makes us an ideal partner to develop next-gen power electronics for the 5G, EV, and clean energy markets?
Yeah, sure. LTTS has been working in power electronics for a long time. We are a part of L&T, and L&T had a strong manufacturing practice in drives. So LTTS for last more than 30 years has known the importance of power electronics, and hence has also invested in the power electronics in terms of the labs or the skills, so on and so forth. To start with the labs, LTTS had a lab of 100 kVA in one of their old facilities, but last year we moved to a new lab with a higher power rating of 250 kVA, and this lab is equipped with dyne setups which are controlled through AFE to test the motors and drives. The reason we are controlling it through AFE is to feed the power back to the grid, so that we don't waste the power which is being burnt in the load. Rather, we only feed the losses. Number two, these labs are now also equipped with pre-compliance for EMI, EMC, thermals. In fact, some of the equipments what we have, like a thermal oven which is 8 meter cube, can enable us to do a lot of thermal testing, do a thermal halt and HAAS for multiple devices under stress. In addition, the pre-compliance we can test for conducted emissions in our own facilities in Mumbai. We also have a radiated emissions test facility in Mysore. In addition, we have associations with ULs and TUVs of the world, but we are also associated with a lab which is a government lab in Mysore called Lahari, which is fully equipped to handle any kind of a compliance for EMI and EMC. In addition, we have a very strong association with the universities like Indian Institute of Sciences, IIT Kanpur, IIT Mumbai, where we work with them for a lot of projects in power electronics.
Thank you so much, Atul. I think that was a fascinating perspective into the opportunities and possibilities in power electronics. And to all our listeners, thanks for tuning in again. To listen to the other episodes of our Engineering for the New Reality podcast series, do visit our website at www.ltts.com. Thank you and have a great day.